One common comment, or even complaint, heard about experiments done with farmers is that the results can be noisy or variable. In this video, I introduce the idea of turning some of that noise into useful information. Data from on-farm trials are too variable. There is a lot of noise in the data. The coefficient of variation is very high, and you will not get significant treatment effects because of the variability. These sorts of comments are commonly heard about on-farm trials, and they're used as an argument against using them. At least, against using them for research, rather than only as part of an extension project. It's true that results from trials involving many farmers do tend to be variable, with treatment effects apparently different on different farms. It's also true that if you use conventional methods of analysis and interpretation that focus on the average differences between treatments across the whole experiment, and whether they are significantly different from zero, then the results can be disappointing. But I hope to show you how an alternative view of the data can actually give more useful results than a simple look at means, and make use of this variation. Some of the noise, or unexplained variation, is turned into information. I'll also briefly explain the implications for designing better experiments with farmers. The piece of advice in the last comment here, to stick to a few farms with several replications on each, turns out to be precisely the wrong solution. Look at this simple example of data from a trial. It's far too small for a real experiment from which you could draw conclusions, but it illustrates the idea. There are 4 treatments or options compared on 4 farms. Crop yield was measured. Farm 3 didn't test option A, but that doesn't matter. If you do a standard analysis of variance, assuming farms are blocks, you find that there is no evidence of a difference in treatment means. The p-value for the test is large, and the coefficient of variation, which is the residual standard deviation as a percentage of the mean, is huge at 83%. But you don't need these statistics to see the problem. Take a look at the data. Actually have a look now. Pause the video and look to see if there's any consistency in the yields. Did you pause? Good. You probably saw that there is no consistency in the differences between the yields of each treatment across farms. For example, treatment A does well on farm 4, but poorly on farms 1 and 2. Consistency of treatment effect is what is measured by the F-test for treatments, and here there is no consistency. The overall means are not very different from each other. The standard analysis would stop there, and researchers would go and do something different. However, let me now tell you something else about these farms. Farms 1 and 2 have sandy soil, while farms 3 and 4 have clay soil. What do you notice now? Pause the video again and take a look at the data. What did you see? There is now some consistency in treatment effects. In the sandy soil, treatments B and C do well, whereas on the clay soil, it's A and D that have the best performance. There is a treatment by soil type interaction, which means that the treatments do not behave in the same way on different soil types. It shows up as a highly significant p-value if you do the test, and when you allow for the interaction, the coefficient of variation drops to 28%. So, rather than simply having a lot of noise or unexplained variation in the data, we have a refined result that shows how the treatments behave on different soil types. Now, this is far more relevant to the farmers than overall averages. It shows that you need to use different treatments depending on what soil type you have. I'm not going to explain how to do the analysis here. Instead, I want to look at the design implications for this idea of moving from noise to information. Here's a real example of the effects of different soil fertility treatments on maize yields on 31 farms. I've colour-coded the yields with green low and red high. It helps show the patterns. The first column gives the control treatment, and that's the farmer's current methods. They're nearly all low yields. The other columns show the effects of 6 different systems, and the results are very variable. Sorting the rows of the table makes it clearer. There are a group of farms that show good response to the inputs. Another group shows mixed response, and a third group are generally unresponsive to any of the soil fertility strategies. What's going on here? Discussion with the scientists suggested that the differential of responses might be due to differing levels of initial soil organic carbon. Further, discussion with farmers suggested that it could be due to the quality of plot management. More generally, ideas for the explanation of such differential effects can come from both local and scientific knowledge, from careful observation of the field plots during the experiment, and from further data analysis. Data analysis will confirm if these are indeed the explanations, but that analysis requires 2 things. It requires you to have the appropriate data, and have an experimental arrangement that will allow you to analyse the data. So, we need to think about how the study is planned and designed. If we have the hypothesis, or guess, that the effect of treatments depends on the 2 factors of soil organic carbon and quality of management, and both of these vary between farms, then the table of means we need to present in the results is this one. And among farms in the same row of the table, we should then have good consistency effects. If you've measured these 2 quantities of soil organic carbon and quality of management, you could do the analysis and find out. Hence, part of the design should be planning to measure the soil organic carbon and the quality of management. But you might be unlucky and find that you have very few farms in 1 or more rows of the table. Hence, if you had these hypotheses before you started the trial, or if you're planning a follow-up experiment, then the ideal way your total of about 32 farms would fall in the table is like this, with an equal number of farms of each type. Soil organic carbon is something that changes slowly, so you could determine it before the start of the experiment, and make sure you had enough farms of each type. The quality of plot management may be something that you don't know before the start. So maybe the best you can do at the design stage is this, and hope that you get a decent number of farms in each management group. And of course, you must design measurement, so that at the end of the season you do know which management group each farm or plot falls into. A possible constraint to using this design idea is that the interaction with farmers is a participatory process. Farmers are not usually recruited or sampled to take part in trials. They're typically members of farmers' groups, and they take part in the trial as part of group activity. What if such farmers don't include those with low soil organic carbon? This wouldn't be surprising. Most farmers' groups don't represent a random cross-section of local social or ecological conditions. But you do have some options to try and achieve a good representation of the farmer population that you are interested in, with the aim of getting a good number of farms of types needed to get useful results. Discuss your requirements with farmers. Find out where they fall in the categories needed, and then try to recruit farms or fields of types that are underrepresented. If, in the end, it's not possible to find, for example, enough low soil organic carbon fields, then you must accept that your results will not be universally relevant. They will only be relevant to the types of farms present in the study. For example, if you did not have enough low soil organic carbon farms, then your results will be valid only for farms with a high soil organic carbon, and you would not be able to make any statements about the effects of the treatments on low soil organic carbon farms. The main point here is to plan, and to understand the heterogeneity of farms and farmers that are included, rather than just leave it to chance. Understanding the differences between farms is part of the subject for the next video, where we discuss the issue of using farmers as replicates.